Adding scalars together is easy. After all, scalars are just numbers. Mass is an example of a scalar quantity. When a boy of mass 50 kilograms steps onto a scale measuring mass, it will register 50 kilograms. Add on 5 kilograms more and the scale will read 55 kilograms. Because mass is scalar, we just have this sum. 50 kilograms plus 5 kilograms equals 55 kilograms. You just add the 5 kilograms onto 50 kilograms because scalars are just numbers. Now temperature is a scalar quantity too. So one particular day the outside temperature was 20 degrees Celsius, and if the temperature rose by 10 degrees it would become 30 degrees Celsius. Once again, because temperature is a scalar, you just add on the numbers. 20 degrees Celsius plus 10 degrees Celsius equals 30 degrees Celsius. Now adding vector quantities together is much harder. You have to take into account the vector's magnitude and direction. Now that's best done by arrows. So let's see how it's done. Here is an example of adding vectors together. In this case it is the velocity vectors of the wind and an airliner. Now an airliner is travelling with a velocity of 500 kilometers per hour to the east. Check the little compass. Now all velocities are measured relative to the ground below, which we consider as not moving. There is a wind blowing from the west, and this means it will have a velocity vector relative to the ground of 300 kilometers per hour to the east, if you check the compass. Now the big rule about adding vectors is that the nose of one vector must join with the tail of the other. This is the big rule we have to obey in adding vectors together. Okay, let's go and arrange the vectors. Now let's add the two vectors together, remembering the important rule that the nose of one vector must touch the tail of the other in order for the two vectors to be properly added together. So we start off with the 500 kilometers per hour to the east vector of the velocity of the airliner. And to do that, we put our start down here, just the very same way with displacement. We put our start here. And we use a ruler to draw a scale diagram of that vector. It's 500 kilometers to the east, so we're going to use a scale of 1, 2, 3, 4, 5 centimeters in this oversized ruler, and one of these centimeters is going to stand for 100 kilometers per hour. So when we draw the velocity vector in, it's going to look like that. 5 centimeters on your ruler. Now that's the first vector done. Now what about the wind velocity vector? Well, this is this one here, and we know that when we're adding these two vectors together, we only can add them such that the tail of one touches the tail of the other. So in this case, because it's all going to the east, then all we have to do is draw a line representing the vector with our ruler. So we put our ruler here, and we have to draw an arrow represented by 300 kilometers. So that will be up to the 3 centimeters line like that. And that's our two vectors put together in a position so that they can be added together. And we'll call that the finishing point there. Now remember from our study of vectors for displacement, the resultant vector is always from the start to the finish. So in this case, this big red vector here represents the resultant velocity of that aircraft relative to the ground. And you can see from the length of it, it's going to be about 8 centimeters in length, which translates as 800 kilometers per hour, and it's heading towards the east. So there is a resultant velocity of the aircraft relative to the ground, 800 kilometers per hour to the east. It's going much faster relative to the ground than it would be if there was no wind there. And that's why pilots who are flying across the Atlantic from America to Britain really want a tailwind, a wind which is pointing in the same direction, to make their speed or magnitude of velocity, which is called the speed across the ground, to be much bigger. So that's our first example. Let's look at another example. So here is a different example. We have the aircraft travelling to the east with a velocity of 500 kilometers per hour to the east relative to the ground. But this time the wind velocity is different. It's coming from the east, which means it's pointing to the west, and the wind velocity is 300 kilometers per hour to the west. Now, like all vector diagrams, we must arrange the vectors properly in order to find the resultant velocity. So we begin with our start point, as we do with all vectors, and we're going to draw a line to represent the velocity vector of the aircraft, which will be 500 kilometers, and in our scale 1 centimeter on this oversized ruler is going to stand for 100 kilometers per hour this time. So if we draw in our vector, we should get a vector line like that, reaching up to the 5 centimeter mark on the ruler, and that represents 500 kilometers per hour pointing towards the east. Now our next vector is a bit of a problem because it's pointing the wrong way. Now the rule is we can add vectors like that because that's nose to nose, and we can add vectors like that because it's tail to tail. So we must arrange the vector so that the start of the blue vector, which is the wind velocity, is nestled into the nose of the aircraft's velocity. It's the only way we can add them together. So we must draw a vector of 300 kilometers starting from the nose of the aircraft's vector. So if I slide that ruler along and I get to there, then if I draw a line, then the blue line will represent the vector, and it must be in that position, like that. I've just drawn it slightly below it so as you can see it. 3 centimeters in length, pointing to the west. So there's the two vectors in their important position, all ready to be added together. Now I know fine well that that's going to be the finishing point here. So the resultant vector is always from the start to the finish, and we can draw that in from start to finish like that. So the green vector is the resultant velocity, and you can work out what that is because from the start up to the top vector here is 500, and then really you're going back 300. So what we're going to have here is a resultant vector of 200 kilometers per hour, and it's pointing to the west. So the resultant vector is 200 kilometers per hour to the west. It's very important to realise that when you're adding vectors together, one vector's nose must touch the tail of the other. And because they're in a straight line, I've slightly moved that down a wee bit so you can see the two vectors added together. There is the resultant, 200 kilometers per hour to the west. Which means if you've got a wind blowing towards you, the aircraft is going to go a lot slower over the ground, and that will make the journey time much longer. So there we go, we've solved that by adding those vectors together. Here's our last problem about adding vectors together. This time the vectors are at right angles to each other. We have an aircraft travelling in due north of 500 kilometers per hour velocity due north. It's encountering a wind coming from the west, which means it's pointing to the east, with a magnitude of 300 kilometers per hour. So our job is to arrange those vectors, find the resultant, but we have to arrange them in the proper fashion so that the tail of one vector touches the nose of the other. So we start with our start position here, and our first job is to draw in the 500 kilometers per hour vector of the aircraft. So we use our ruler for that, and we set the ruler here, and we draw in our vector with the ruler. And because we know our scale, it's 100 kilometers, 200, 300 kilometers, 400 kilometers, 500 kilometers per hour. So that's our vector done. Now we have to add in the 300 kilometers per hour vector. Now it's at right angles to this vector, so we have to use a set square or the edge of your ruler and make sure that that's going to be the right angle part in there. Now I can draw a kind of faint line for that, then just draw a kind of faint line, but what I'll do just is draw in a little dot to show you that it must be along that line to give us a right angle to our velocity vector of the aircraft. So I can take my set square and move it away, and I can bring my ruler out, and I can then change my ruler to the horizontal position, and I can now draw in the vector of the wind. So I set my ruler up like that to 0. It's going to be 300 kilometers long, so it's going to be from here, my ruler line is going to be here to there, and that's the velocity vector of the wind added in the right position. Why is it in the right position? Because the nose of the velocity vector of the aircraft is touching the tail of the velocity vector of the wind. They're adding correctly. And that will be my finishing point for my diagram. The resultant vector is always drawn from the start to the finish. It always points from the start to the finish. So here is my resultant vector of the velocity of the aircraft relative to the ground. So all I have to do now is measure the length of that and measure the angle from north, and I have the resultant vector. So we'll measure the length of it first of all then. So to measure the length of it, I arrange my ruler like that, make it parallel to it, and move my ruler down, put it onto the start, and give it one wee turn round to about here. And I can see that the distance of it is 5, the length of it, sorry, is 5.5, 6, 7, 8, about 5.8 centimetres. Now that 5.8 centimetres will in fact result in a vector having a magnitude of 580 kilometers per hour. So it's going to be 580 kilometers per hour is going to be its magnitude. Now what about its direction from north? Well, I draw in the north line. I go from the start and draw in my north line. There's the north here. And I take my protractor and I make sure that the centre of the protractor is put over the starting position. So I do that over the starting position with the 0 angle going straight up the north line, and I can see that the angle it makes between the north and the resultant vector is about 30 degrees. In fact, it's 30 degrees. So I can move my protractor out of the way and I can put in the angle now. It's 30 degrees, and that's going to be 30 degrees there. So the resultant velocity of that aircraft when the wind is blowing that direction will be 580 kilometers per hour with a bearing of 030 degrees from the north. That will be my resultant vector, the resultant velocity of that aircraft. So the aircraft's going to be swept in that direction away from relative to the ground. Here's a question for you. Which direction should the plane fly if it wanted to keep a northerly track? You think about that one.